So what we've just witnessed with the substitution and elimination, it's not a hard process. If you only have two equations, it's pretty short. When I threw in that third equation, what happened to the length of your problems? It got a lot longer. What do you think would happen if I threw in 4 or 5 variables? It's going to get exponentially longer. So there is another method for solving systems, and it's kind of like a trade-off. If you only have one or like 2 or 3 variables, substitution elimination is probably going to save you time. Okay, but if I throw in 4 or 5, this other method only gets slightly longer, whereas substitution and elimination just explodes, and it creates a lot more work. Now, I'm not going to start out giving you problems with 5 variables in them. So I'm teaching you a process, and it's going to seem silly because you could solve the same problem I'm giving you with substitution or elimination, and it would be faster. But if I were to give you that problem with 5 variables, this one would be way, way, way shorter. So it has a time or place, but I just can't start you at that place. Does that make sense? All right. So we are going to start talking about matrices, and that's kind of be what we end this year with. So we're going to talk about properties of matrices later on, some solving equations with matrices. Today we're looking at how to use a matrix to solve a system of equations. So a matrix is basically something like this. It's just an array of numbers. Okay, so it might look something like this. You don't see the variables in that. Each of these numbers is called an element of a matrix. It's just an assortment of numbers. And matrices can be used anytime you have a large amount of data to organize. We are specifically looking at matrices that match equations, systems of equations, but they have other places anytime you have a lot of different numbers. So when we're looking at this, these are called columns. So the vertical ones are columns. Horizontal ones, what do you think those are called? Rows. If I ask you about the size of a matrix, you give me rows by columns. So the size of this matrix, how many rows do we have? 2. How many columns? 3. So this is a 2 by 3 matrix.
Do you want us to write matrix with a 2 by 3? You said it's a 2 by 3 matrix. Do you want us to write matrix?
You don't have to. You can just say 2 by 3. Right. Any questions so far? So we are going to take our system and write it in a matrix. So I'm going to show an example of how that's done. This is a specific kind of matrix. This is called an augmented matrix because it has an equal sign. The vertical bar represents your equal. So you basically, each equation becomes a row in your matrix. And we line things up. So my first columns, all of these represent what variable? X. The coefficient of x. My second column is my coefficient of y. The third column is my coefficient of z. Then we have a vertical bar for the equals and then our constant. So this is an augmented matrix. Great point. Everything has to be set the same, so constants have to be on the right hand side of the equal sign. If you don't have a variable, then we use a 0 for it. What's the size of this matrix? 3 rows, 4 columns. So this is a 3 by 4 matrix. That can tell you, like, specific numbers, so I could use that to refer to a specific number in the matrix. So if I said row 3, column 2, what's the number in row 3, column 2? 1. If I said row 1, column 2, what is that? 3. If I said row 2, column 3, -1. So you can use that to refer to specific numbers as well. All right, so far so good? So the first thing we're going to do is just practice taking a system and writing the matrix that would match it. So if I look at this first one, how many rows is my matrix going to have? 2. You get a row for each equation. So my first row, we would have the 3 for the x, then -4 equals -6. Second one is 2, -3, -5. What's the size of this matrix? 2 by 3. Don't include any variables in the matrix. It's just an array of numbers. Okay, so my second one, we have 3 equations, so we get 3 rows. The first row, we have a 2x, -1y, 1z equals 0. If you're Depending on what your variables are, we just usually go alphabetical order when we set up our columns. So you do have to make sure that you line them up. We have an X column, we have a Y column, we have a Z column. So if your equations were jumbled up and things were in a different order, you need to make sure you line up those coefficients. What would my second row be? We have a 1x, we have no y, we have a 1z. What would I have to do with this -1? So you have to move those constants over. This one is x plus 2y equals 8. So my matrix would be, or my row would be 1, 2, 0. Let's try this one. So we do have to think about moving that constant over. Oh. So first row, 2, 3. A few of you put a 0 for the z. Which is technically not wrong, but you'll notice that entire column is zeros because we don't have any z's. So if you don't have any of them, you can drop out that column altogether. So you only have to include columns for the variables given in the problem. Is that okay? I'm going to put 2 problems up here. These are matrices, and I want you to see if you can write the original equations from the matrices. So what's the first equation? And next one? Okay, what's the size of this matrix?
2 by 3.
All right, what's the size of this one?
That was a 3 by 4.
What's the first equation?
3x minus 5z equals.
Second one?
2x plus 2z equals 8.
Okay, you have a 0y, but you don't need to include that in your equation. And the last one?
Y plus z equals 0.
All right. Are we okay with those? So now, we are going to talk about row operations. So these are legal things we can do to a matrix. It all kind of relates back to substitution and elimination, mostly the elimination piece. So think about if you're going to eliminate a variable, we can multiply or divide our equation by whatever we want, and then we add them together, right? So that's essentially what these row operations are. It's just a shorthand where we don't have to include the variable along with it. So these are the legal things we can do when we are using matrices to solve systems, and you want to write this down. I'll let you write and then I'll talk about them. Okay. So the first thing is we can swap rows. All that's doing is basically, if you think about a row represents an equation. Does it matter which equation is on top? No. So if it's more convenient for us to have a different one on top, we can do that. We just flip entire rows. That's legal. Second thing, if you were going to solve this by elimination, you would probably start by taking that 1 times 2, right? So we can multiply by anything we want except 0. Do we ever just take the whole row times 0? No. So just like with elimination. The last thing, if you were doing elimination, you would multiply it by 2 and then add those equations together. So we can add rows together. So we can switch them, we can multiply by anything, and we can add rows together. So here is an example. We're going to practice some individual row operations. So I want to do the row operation. Row 2 equals. So we start out, it'll usually be a capital R telling you which row you're changing. And then it'll tell you how you change it. So my new matrix, I'm changing row 2. So row 1 stays the same. To get my new row 2, I'm taking -3 times the first and adding it to the second. Okay, so if you need to, you could write this out. If I took the first row times -3, then I would have a -3, +6, -6. The second one stays, so this is just kind of my work over here. So if I add those together, -3 plus 3 is 0. 6 plus -5 is 1. And -6 plus 9 is 3. So that is my new row 2. If you don't want to show the work out to the side, that's up to you. You could say, okay, I'm going to do -3 times 1 plus 3, that's 0. -3 times -2 is 6. Plus -5 is 1. -3 times 2 is -6. Plus 9 is 3. So it's just kind of up to you and how comfortable you are with that. Does everyone understand that? I'm going to put one up here and I want you guys to do. So do this row operation. So which row gets switched? 2. So row 1 stayed the same. Okay. So you're doing -2 times the number in row 1 plus row 2. You could have worked it out to the side, but it's -2 times 1 plus 2, which gives us 0. -2 times -3 plus -5. If I did -2 times -2 plus 5, 3. Are those okay? Now let's try to come up with our own row operation. So I want to write a row operation that will result in the augmented matrix having a 0 in row 1, column 2. So row 1, column 2, this number. I need to make that a 0. So when we do this, we will draw arrows usually to show we're going to a new matrix, and we'll describe our row operation here. It starts by telling us which row we're changing. Are we changing row 1 or row 2? Row 1. So capital R1 equals. And then you're going to tell us how to do it. Our legal moves are to add rows and to multiply. Okay, so I can't just say I'm going to add 2 to everything. I can't add a single number. I can add a multiple of another row. So let's start with row 1. I'm on row 1. It's a positive 2, so I'll have to add something. What would I have to add? 2 times row 2. Let's see if that works. So row 1 doesn't change, or sorry, row 1 changes, row 2 does not, so we leave the row 2. You have to do this to every number in row 1. So row 1 plus 2 times row 2. So this is like 1 plus 2 times 0. And we get 1. Next one, the number in row 1 is a -2, plus 2 times the number in row 2. So -2 plus 2. Next one, row 2 is a 2, plus 2 times the number in row 2. So 2 plus 6 is 8. And we got a 0 in row 1, column 2, just like we were supposed to. All right. Is that okay? So all of this is kind of leading up to how we are going to solve a matrix. So we're doing what's called the Gauss-Jordan method. And in this method, our goal is to use row transformations to reduce the matrix to a diagonal with ones along the diagonal. Like this. So we want ones on the diagonal, zeros everywhere else. Think about why that's helpful. This first equation, that would be like saying x equals a. The second one would be y equals b. So if you have a 1, that's your variable. If all the other variables are 0, that's the solution to the system. So our goal is to get ones on the diagonal, zeros everywhere else. So if I had this one, write the solution for me. First equation.
X equals 1.
Second one.
Y equals 2.
And the last one.
0 equals 3.
Does 0 equal 3? So what does this tell me about my system? So anytime you have all zeros equals a number, then that system is inconsistent. And if that happens in the middle of the problem, there's no need to keep going. You've already found that part, so you can stop and say inconsistent. All right, so our strategy. We have to be very careful about how we do this. We want ones on the diagonal, but if you do things in the wrong order, we have to add rows together to get zeros, and so we'll end up undoing our work. So we have to go in a very methodical process for this. So step 1 is we need a 1 in row 1, column 1. Step 2, we get everything else in column 1 to be a 0. Then we move to row 2, column 2. So we get a 1 there. Then we get everything else in column 2 to be a 0. Then we move to row 3, column 3. Get a 1, get zeros from there. So we get the 1 in the column, then we get the 0 in the column. And we move to the next one. Okay, so first thing, if I want to use a matrix to solve this system, we have to write our matrix. So 1, 1 equals 8. 1, -1 equals 4. All right. First step is a 1 in row 1, column 1. But we have that already. So we don't have to do that. What did I do? Okay, so we have our 1, so we're good there. Then we have to get zeros for everything else in the first column. So we need to turn this into a 0. Which row am I changing? Row 2 equals. Okay, let's just start with row 2. There are different ways to do this, but I'm going to kind of go with a method where it's the same every time. So I'm starting with row 2. It's a positive 1, so if I'm trying to get that to be a 0, do we have to add or subtract? Subtract. And what would I need to subtract from it? Well, the minus gives me the negative, so I just need to subtract row 1. Okay, so row 1 didn't change. Row 2, I'm doing 1 minus 1, which is 0. -1 minus 1. 4 minus 8 is -4. All right, column 1 is done. I have my 1, I have my 0. What's the next step? Yep, we want the ones on the diagonal, so we need row 2, column 2 to be a 1. What would be the easiest way to turn that into a 1? So row 2 equals row 2 divided by -2, or you could say times -1/2, means the same. So row 1 didn't change. So we have 0 divided by -2 is still 0. -2 divided by -2 is 1, and -4 divided by -2 is positive 2. What's the next step? We have our 1 in column 2, so we need this to be a 0. So we are changing row 1. Row 1 equals row 1. What will I have to do to that? We're trying to make it a 0. Minus, you can't just subtract 1 from everything though, but we can row 2. So 1 minus 0 is still 1. 1 minus 1 becomes 0. And 8 minus 2 becomes 6. Now what? Yeah. The first equation says,
X equals 6,
and the second one.
Y equals
Okay, and we can check ourselves. 6 plus 2 equals 8. 6 minus 2 equals 4. So we have the right answer. So our answer is order pair 6, 2. Now I know this is longer with 2 equations, but I promise if I put 4 up here, it would only add a couple steps to our matrix process, whereas elimination, it would probably triple the amount of work.
2. Why does this feel like a math version of like chess or something?
It is kind of like a logic and reasoning piece. All right, is that okay? Let's do one more for today. I know I'm talking all class period today.
Why could you do this? Why would you do this?
But I don't know that I want to go in order. I might do. Yeah. I can do this one.
So what would happen for like how would it happen that you would like end up getting all zeros on one row?
So when you add rows, everything would cancel.
Okay.
So you.
Okay.
So my first row would be 3 negative 4 equals 1. Second row, 5, 2 equals 19. All right, what do we need first?
A 0 in row.
Not a 0 though.
Or 1.
A 1. So how would I get that to be a 1? Okay, easiest option to get a 1 is just to multiply by the reciprocal or divide by that coefficient. Same thing. So row 1 divided by 3. Okay, it's going to give us fractions, but we're big kids, we can handle it. So 3 divided by 3 is 1. Do not go to decimal form. Keep it in fractions. We didn't change row 2. All right. Now what do we need? So we're changing row 2. Start with row 2. It's a positive 5, so we have to subtract 5, but you can't just subtract a number, so it has to be 5 times row 1. So row 1 didn't change. Okay, if you need to, you can write it out. You can just grab your calculator and work through it. You're doing 5 minus 5 times 1. So 5 minus 5 is 0. Then we have 2 minus 5 times negative 4/3. What's that give us?
A number between negative infinity and positive infinity.
Really? About 26/3. Last one. Row 2 is 19 minus 5 times row 1 was a 1/3. 52/3. All right. Not pretty, but we're getting there. Which row? What are we changing now?
Could we like go ahead? Yeah. Could we go ahead and change row 2 and just like multiply by the reciprocal?
Okay, we need a 1 in row 2, column 2. And the easiest way to get a 1 is to multiply by the reciprocal. So it would be 3/26, row 2. Or you could say divided by 26/3. Same thing. So 0 times anything is still 0. 26 over 3 times 3 over 26 is 1. 52 over 3 times 3 over 26 is 2. Okay,
So kind.
we are one step from the answer. What's our final thing we need?
Get rid of the 4 thirds.
We need a 0 here. So easiest way to get a 0, we're changing row 1, so start with row 1. It's a negative 4/3, so we have to add 4/3, but you have to take it times a row, so it'd be plus 4/3 times row 2. So row 2 didn't change. So row 1. 1 plus 4/3 times 0 is still 1. Negative 4/3 plus 4/3 times 1 is 0. 1/3 plus 4/3 times 2 is 9 over 3, which is 3. So x equals 3, y equals 2. Any questions there? Okay.
So whenever you're doing that, would generally, like when you get to like the last step and you have something like that, you just want to go with something that already has like those things?
Yes.
Okay.
So we are going to be practicing a lot more of these. I did go ahead and post a handout on Google Classroom, but it is not going to be due tomorrow. So I may add at most one more question to it tomorrow, but if you want to start it, you can. The first few are more of just the row operations, writing the matrix. The last 2 questions are like what we just did, but you probably need more practice before you're ready to do one of those on your own.